One of the most important applications of the derivative is its ability to tell us where a function has a max or minimum value, in other words, an extreme value, which is something that in your math career at this point you probably just use calculators to do. But calculus is going to tell us that information, and it's the derivative that tells us that. So first, just some definitions. If f is a function with a domain D, then f of c is the absolute maximum value on D if and only if, informally speaking, if and only if it's the highest y value in the domain. So to represent that as the highest y value in the domain, we want to say that it's bigger than other y values, and we want to say it's bigger than all y values. Now I'm gonna sneak in a less than or equal to here because we want to account for the possibility that there may be other locations on the graph for which that maximum value occurs. I mean, take the sine graph, for instance. The graph of sine has a maximum value at 1, which occurs multiple times. So we really can't say that 1 is bigger than or equal to all other y values. I'm sorry, we can't say it's strictly bigger than all other y values. It's bigger than or equal to, right? Because it actually equals these other outputs, or at any other time that the sine graph equals 1, it's sort of a tie. So f of x is less than or equal to f of c for all x in D. And similarly, an absolute minimum on D if and only if f of x is bigger than or equal to f of c for all x in the domain. Okay, so I have a graph here. We can kind of use some, we can use it to locate where we would find maxes and mins, absolute maxes and mins visually. So it looks like we have an absolute max here at D for y equals f of x, because f of D is bigger than or equal to f of x for all x in that domain. So I'm going to say that's an absolute max. And the absolute min looks like it occurs over here at A, because f of A is less than or equal to f of x for all x on this domain. I probably should have stated the domain here, based on my picture, is from A to E here. Alright, you may have y values that are maxes and mins, and they may be maxes and mins in their immediate neighborhood, but maybe not necessarily the absolute max or mins. In other words, they may not be bigger than or equal to all other y values in the entire domain, but maybe just in their local neighborhoods. So we define those to be called local maxes and local mins. Sometimes they're called relative maxes or relative mins. So we'll say that if C is an interior point of the domain of a function, then f of C is a local maximum value at C if and only if f of x is less than or equal to f of C for all x in some open interval containing C. Okay, so not in the entire domain, but just some open interval containing it. And a local min if f of x is bigger than or equal to f of C for all x in some open interval containing C. So let's identify our local maxes and mins on our graph here. Looks like I've got a local min here at C, because the y value is, or f of C is less than or equal to f of x for all x in that immediate neighborhood. And looks like I have a local max at B. And it looks like we can also identify this absolute max as a local max, because if it's if f of d is bigger than or equal to f of x for all x in the domain, then it's obviously going to be bigger than or equal to all f of x in its immediate neighborhood as well. We can also identify endpoints as local maxes and mins, even though it wasn't defined up here in the definition. So there's an absolute min here at A, that's also a local min, where its neighborhood is just the neighborhood of this of A is just obviously defined to be to the right of A. And then we can talk about there being a local min here at E. All right, so there's definitions of absolute maxes and absolute mins, local maxes and local mins, and in future videos we're going to use those ideas, or we're going to find those using calculus, using the derivative. One of the important properties of continuous functions on closed intervals is that they'll always have a max or a min. So if I try to sketch, I'm going to here sketch a function on a closed interval, and it's like a game. My game was going to, the purpose of this game is going to be to try to sketch a graph on the interval a to b that's continuous and it doesn't have a max or a min. So it shouldn't take you too long to see that no matter what you do, so like let's say I want to try to avoid making this have a min, so I'm just going to have it keep going down, but at some point I need to stop, and now we can see that it has a min right here, an absolute min there at an endpoint. Right, so I failed at that time. If I tried, let's try making it not have, let's say I don't want it to have the absolute min at the endpoint, so that means I would probably do something like this. I'm going to say, okay, well, I'm going to go up, but now it has a min on the at the endpoint on the left, so I'm going to make it come down now. But if I go down lower than it, okay, so now that left endpoint's not the absolute min, but eventually I have to stop, and this time my absolute min again happens at this endpoint here. And notice both of these also have absolute maxes, right? We have an absolute max here, and in the blue graph we have an absolute max here at the endpoint. Right, and I should label these. And there's my absolute min. Here's my absolute min. All right, so that was. If you play that game a few times, you'll find that there's nothing you can do. There's no way to avoid giving these functions absolute maxes and absolute mins. Now, it's important that we're just restricting our attention to functions that are continuous on closed intervals. Because, for instance, look at this situation. Let's say I sketch this graph. So I'm saying that's a function, and it's not it has no defined y value at a and b. F of a and f of b are not defined. So this actually has an absolute min, incidentally, right here, but it has no absolute max. The reason it has no absolute max is because if you go back to the definition of an absolute max, a function has an absolute max at c if f of c is bigger than or equal to f of x for all x in the domain. In other words, can you find a highest y value? You cannot find the highest y value for this graph. And like let's say, for instance, like that those both have those holes both occur at 1. A lot of students say, well, just take the number right below 1, and let's call that the absolute maximum value. The problem with doing that is, in the real number system, you can't order numbers like that. You can't find a number right before 1. You know, if you try, some students would say, well, what about 0.9? Well, there are numbers in between 1 and 0.9. There's a number bigger than 0.9 that's less than 1, like 0.95. And so then you'd say, well, okay, how about 0.955? But of course, there are numbers in between 0.955 and 1 as well. And so no matter what number you choose, I'll always be able to find one bigger. So that has no absolute max. And similarly, I could draw a graph that looks like this. And this, for similar reasons, would have no absolute min. So it is important that your graph is defined on a closed interval, right? And these are continuous on open intervals. So the extreme value theorem doesn't apply. Okay. And the other thing is that it has to be continuous in the interior, of course, because I could easily give you let's just sketch a graph here with an asymptote at C. We can see that this is not going to have any absolute max or min values, because any y value you choose, I'll always be able to find one bigger by traveling along this curve towards the asymptote from the left. And any y value you give me as a candidate for the absolute min, I'll always be able to find one smaller by traveling along the curve on the right here to the left of the asymptote. All right. So all that forces us to restrict our attention to functions that are defined, that are continuous and defined on a closed interval. So the extreme value theorem says that if f is continuous, on a closed interval a to b, or ab, then f has both an absolute max, we'll just use max, and minimum value. On that interval. So that's the extreme value theorem. Remember that, make sure that your conditions apply, right? It has to be continuous on the closed interval, or continuous on the closed interval. I guess those are the two conditions.